Hi, it's Mr. Canada, and we're back with working on vectors, and we're looking at diagrammatic representations. Okay, so all this stuff is going to help us when we actually start solving and talking about vectors in more detail. So, consider the arrow that we have just under there. We have a tail and a tip. Okay, so this we're going to use. I'm going to call it tip to tail lots of times, right? That's how we're going to add and subtract. So, our tail is our starting point, our tip is our end point, okay? So notice that we have a direction, right? Our arrow points in our direction, and our magnitude is just how long it is, right? So if we consider the vectors below, A, B, and C, well, A, notice that if we start at A, we go 2 to the right, right? Just like with translations, and then 3 up, okay? So we can break them into components as they're called, AX and AY, the X component and the Y component of A. I typically denote them that way. You do not have to, but I find that it's just very clear to myself, let alone everybody else, what I'm actually talking about, especially if you're talking about many different variables on a page. So similarly, you can do the exact same thing with CX, CY. So notice that we're just starting and we trace along, adding tip to tail. We'll talk about this more when we actually get to addition of vectors. Okay, so that breaks us up into components and talking about what they are. So continuing on, we're going to talk. We have negative vectors, right? So a negative vector, they have the same magnitude or size, however the direction changes. So if we're doing this mathematically on the left, you'll notice that A and negative A, the only thing that differs is a sign change. So positive 2 becomes negative 2, positive 3 becomes negative 3. And then on our diagram, notice that the arrow is just going to switch. It doesn't matter that our position is at a different place. It just matters that, hey, they're the same length, which they are, so but the arrow has completely swapped directions. So, therefore, it's a negative of that vector. Now we're talking about vector addition / subtraction. So, we're going to talk about adding and subtracting vectors by drawing them tip to tail. So, notice with A plus B, I started at A down here. I traced along, and then after that, I drew in my B, and then my resultant A plus B was from the start of A to the end of B. Okay, so that's hence adding tip to tail, right? Because this tip to this tail is how we put them together. Next, okay, we're looking at B minus A. So if we're at B, and then we trace it all the way around, draw it, right? And then we take away A, then we're going to be left with that. Okay. Next, if we have A minus B, we're looking here. And sorry, I actually noticed one little problem right here is that we actually have these in the B minus A in the wrong spot there. So I apologize. That's not actually B minus A. Sorry. That should be B minus A down there, and that should just be B. So I apologize for that. Next one though, we have A minus B. So if we're at A and then we subtract B, our resultant vector is just this guy. So we're gonna get lots of work into that because noticing just by adding and subtracting, we're changing the layout of our question because our vector has to be magnitude and direction. If the direction changes, it's a totally different vector. One thing that's handy with talking about parallelograms during diagrammatic representations is that it doesn't matter the way we add vectors, okay? Just like, because these properties are a bit different. It's not just basic maths, right? But with parallelograms, we can still add and subtract or with vectors, we can still add and subtract in any way. Okay, so A plus B, right? If we're at here and we trace it up to B and then we draw our B vector over, great. But here, if we start, we do B first, and then we add A, we still end up at the same endpoints. We still have the same resultant vector, which is this inside vector here. And lastly, last thing I'm going to briefly talk about is scalar multiplication. Okay, so scalar multiplication, if you're given a vector A, and say we want 2A, well, that's just simply going to be A plus A, right? So it's this it's same direction, just double the length. 3a, triple the length, same direction. 4a, quadruple the length, same direction. You get the idea, right? So